In this problem, we're told that a motor moves with a velocity, VA, is equal to 3t squared. And we would like to figure out the amount of time it takes for this box B to move up to 7 meters. And we're going to say that we start at some position 0. So how long does it take for the box to do that? Two things we should notice from this problem that stand out. The first thing is it's a pulley problem. And this pulley problem has 3 different ropes. So in order to fully define the length of all the ropes, we're going to need 3 equations. The second is that our velocity over here, VA is equal to 3t squared, has this t squared term. So this is not constant. And if we differentiate our velocity with respect to time, we get my acceleration of A is equal to 6t. And in fact, what it turns out is that this is a function of time. My acceleration is a function of time. It's not constant. And that means the kinematic equations of motion, such as the final velocity is equal to my initial velocity plus acceleration plus time, these are not valid and we cannot use them. Instead, we're going to need to use equations like my velocity is equal to dx dt, and we're going to have to do an integration or multiple integrations. So let's look at this pulley, and actually this is connected. It's not just floating there. So this is connected to a fixed point. First part of a pulley problem is always dimensioning the lengths of the moving particles and figuring out a reference point. The reference point I'm going to choose is through this top pulley. Everything right here is constant, so it's not going to change. And seems like it's a good point for the reference line. Second thing is what I need to do is I need to define the positive direction of my problem. And I always define my positive direction as the way that I'm going to be dimensioning the length of the pulleys. So since I need to dimension downward for the length of these ropes, that needs to be my positive direction. Next thing is what I need to do is draw a line through each of the particles that move. So I'm going to have some line that goes through D. I'm going to have some line that goes through A. I'm going to have some line that goes through C. And I'm going to have some line that goes through B. And I'm just going to clean up these lines, make them dashed, just to make it a little easier to see. And then I can draw arrows from my reference point to these lines right here. I just need to be a little careful around the 7. And I just made these lines a little longer as I went down so I can draw my arrows a little cleaner. First arrow I have is going to be to this point. So this length right here is going through pulley D, so I'm going to call this some position SD. The second line right here goes through point A, so I'm going to call this SA. The third line goes through C, so I'm going to call this SC. Should have made this a little bit longer. And my fourth line goes through this, and this is going to be some distance SB. Okay, now I have 3 ropes. I need to calculate the length of each of these ropes. What I do is I start at one side of the rope and work my way to the other. This first rope is a little tricky. I'm going to start at point A because that's what I know. I know the velocity of A, and I'm just going to work my way around the rope like this, calculating the total length. So this first length right here is going to be a length of SA. So let's say this is a length of, let's do it like this. This is a length of SA. Then what is this length right here? Well, this is a length of SD, and this is also a length of SD. So it's going to be SA plus 2SD, and then I've accounted for this entire rope that's blue. And we're going to say this is equal to some constant length L1. Right now, I'm going to be ignoring any constant pulley lengths, like lengths over the pulleys, or lengths that are just going to be constant. Okay, so I have the first pulley. Let's do the second pulley. The second pulley starts here. And when it starts here, what I'm going to have is I'm going to have some length that's going to be this, SC, minus this, which is SD. So I'll have SC minus SD plus this length. And this length right in here is going to be it's not that high. This length right in here is going to be a length of SC. So plus SC. And this is going to be some length L2. I can put these together. This will be 2SC minus SD is equal to L2. And let's do the third pulley. So the third one, I have to do the same thing. I have this length right here minus this length right here, which is SB minus SC. And then I have this entire length, which is SB. So plus SB, and this is some constant length. We'll call it L3. Next thing we need to do, we need to differentiate these equations with respect to time. And the idea is if we can differentiate these expressions right here, we'll be able to relate the velocity of B, the velocity of this mass, with the velocity of A, which is given in the problem. So let's differentiate this. We have, for our first equation, our velocity of A, our velocity of A plus 2 times the velocity of D is equal to 0. Remember, this right here is a constant value. When we differentiate a constant, it goes to 0. The second equation is going to be this one. And for that second equation, we have 2 times our velocity of C minus our velocity of D is also equal to 0. The third equation, it looks like I had forgotten to simplify this. So it's 2SB minus SC, just like we did in the second equation. So when we differentiate that, we'll get 2VB minus VC is equal to 0. Now what we have to do is we have to solve in terms of VB and then keep back substituting this up to figure out how to relate our velocity of A with our velocity of B. Let's do that. And we'll have the first, this third equation, we'll start with that. So we have 2 times the velocity of B is equal to the velocity of C. I bring VC to the other side, and I want to now take this and substitute it into this equation. So I'll have 2 VC. So VC is equal to 2 VB is equal to VD. Again, I brought this VD to the other side of the equation. And this is 4 VB is equal to VD. Now, I take this expression and move it up to this equation. What I'll have is my velocity of A plus 2 times 4 VB is equal to 0. Now, VA is equal to minus 8 VB. Now I've related my velocity of A with my velocity of B. I also have another expression for my velocity of A. So if I equate these two together, what I'll get is I'll get that 3 t squared is equal to minus 8 times the velocity of b. Solve for the velocity of b. I get my velocity of b, or the velocity of this weight, is going to be equal to minus 3 over 8 t squared. That's fine. If I use this relationship I have between velocity and position, so I know that my velocity is the derivative of x with respect to time, or the derivative of distance with respect to time, what I can do is then separate integrate to figure out how much time it takes to move a specific amount of distance. So let's do that. I'll say that my velocity of b is minus 3/8 t squared is equal to dx dt. We'll separate this, so I'll get minus 3/8 t squared dt is equal to dx. Now what I can do is I can integrate. If I integrate this equation and integrate this equation, I need to figure out my bounds. So what is at time 0? Where do I start? I start at position 0. Where do I end? Well, I'm looking for some time, but what is this position? Well, you're going to be tempted to say 7, and in reality, it's minus 7. Why? Because we define positive to be downward. Because we define positive to be downward, our final position is moving upward. So our final position is actually minus 7 meters because it goes against what we defined as positive. So this is going to be a minus 7. Okay, now we perform this integral. This integral right here, let's do this. Minus 3 over 8, that's a constant. Then t cubed over 3, evaluated from t to 0, is going to be equal to x evaluated from minus 7 to 0. These 3's will cancel right here, and we'll have minus t cubed over 8 is equal to minus 7. We need to solve for t cubed. So we're going to say these minus signs will cancel out with each other. We'll have t cubed is equal to 56. And then our time will be equal to the cubed root of 56. So let's do that. So we'll take the cubed root of 56, and we get our time is t is equal to 3.83 seconds. So it will take 3.83 seconds to move this box or this weight up 7 meters.